Okay, welcome back. So here's another video. We're still on Calculus 2, Integral Calculus, and still Module 1, or we're under the integration concepts or formulas. But this time, so Unit 2, we'll now be discussing the power formula. So for integral calculus, or the preliminary discussions for integral calculus, there are a lot of formulas that you can use to solve a lot of different problems. So the key is to develop the understanding of when and where to use these formulas. Okay, so we'll be discussing 7 or 6 formulas for the basic integration process. The power formula being the first, okay, of these formulas. So what is the power formula? But in this unit, our learnings must be first identified. So we must first identify the different components of the power formula, of course, and we must also familiarize ourselves with the power formula itself. Apply the power formula to solve some integration problems. Okay, so these are the goals of our unit, or this video is to teach you how to use the power formula and to familiarize yourself with the power formula. But before we discuss this formula, you just recall first the general properties of the indefinite integrals. So first one, we have the integral of du is equal to u plus c. So this is the definition itself of the integration process, remember. Number two, the distributive property of the integration process. So if there are multiple terms, okay, under a single integral sign, it can actually be distributed to be integrated individually. And last one is that if there is a constant inside the integral symbol, you can actually factor it out. Okay, so these are the general properties of indefinite integrals. We're going to use this hand in hand with the power formula to have a much simpler solution for our problems. So here it is. Here's the power formula. Okay, so if you remember in differential calculus, there is also a power formula in differential calculus. It's actually the inverse of this formula only. So the terms, if you notice, are very much similar. In differential calculus, we are going from right to left. Meanwhile, here in integral calculus, we're using the left to right since they are the inverse of each other. So if you read, so the integral of u raised to n du is equal to u raised to n plus 1 all over n plus 1 plus, of course, the constant of integration. However, this power formula has a limitation. Take note here that n must never be equal to -1, meaning you cannot use the power formula if the n or the exponent is equal to -1. Okay, so we'll clarify this later on. But for now, you need to familiarize yourself with the components of the power formula. Okay, you have your u, a function. These are the terms that contains your variables and other constants. Du, okay, is the differential of the function. So du here is the differential of the function, meaning you're going to apply still the principle of differential calculus when you are solving problems in integral calculus. So it means that you cannot take the subject without any prior knowledge to differential calculus. Or if you have a weak foundation on differential calculus, then you have a lot to catch up on before you can properly, okay, integrate problems. And n is the power or the exponent of your chosen function. Okay, take note that this is a formula. So this formula will give you already the answer on your integration problem. However, okay, in order for you to use this formula, in order for you to go from left to right as the final answer, these components must be first well defined and, okay, present. If they are not, then this formula cannot be used. Okay, again, these components or the 3 parts of the power formula must first be well defined or present. If they are not well defined or present, okay, you cannot proceed to the right side or to the final answer of your integration problem. And of course, the limitation of this formula, this must never be equal to, or the n must never be equal to -1. Okay, so why don't we try to solve the initial problem in our introduction using now the power formula. So we have here the power formula on the upper right corner for easy referencing. So example number 1, let's try to evaluate the integral of x squared dx. So if you remember, or if you've watched the first video, this is the first example for integration that we had. Okay, so how do we solve this using the power formula? So as you approach a problem, you recall the formula that you're going to use. For now, you don't know any other formulas yet. So your only formula is the power formula. So this is the one that we're going to use. Okay. So as I've said before, all of the components of this formula must be present first before we can use it. Okay. That means u, the function itself, must be identified or described, and the exponent must also be identified and described, and then du, the differential of the function, must be identified and described. So let's try to relate now this problem, integral of x squared dx, to our power formula, the integral of u raised to n du. You need to choose, okay, you need to choose the variables that will represent each term here in the problem. So for example, let's try to solve for u. U is the function, of course, as I've said a while ago, that can be now composed of single terms, of binomials, or polynomials. So if you look at u, you look for a function that is your x. Okay, so x is a function, x is a variable, so that gives you the idea that u is x. Okay, so x is the value that you're going to plug in your power formula as u. Next, we look at the exponent of that u, of your x. Okay, so u is raised to n. If u is x, therefore x is raised to 2, so n is now equal to 2, the exponent of your function. Next, we look at the differential of u. How do you get a differential? You differentiate, or you, let's say, derive, right? So look at your u. This is our u. To get du, the differential of u, you must, right, differentiate the equivalent of u in your problem, which is x. And we all know that the differential of x is dx, right? So the differential of x is dx. So du is now equal to dx, okay? These three terms, u, du, and n, must have counterparts in your problem and must be present in your problem itself. If they are not, then the power formula is not valid. Oh, and by the way, if n is equal to -1, you cannot use this formula. But since n is equal to 2, it's okay. Okay, so we now have the equivalent terms of the individual components of the power formula. So we can now proceed with the use of the right side. So here, we simply follow the formula. So u, okay, is x. So here it is. U is x. Our n, right, is 2. But according to the formula, you add 1. If you recall, integration is going up 1 degree, differentiation is going down 1 degree. So since we're integrating, we should be going up 1 degree. So this is n. Our n originally is 2. So that is 2 plus 1, 2 plus 1. All over the same term, n plus 1, but this time on the denominator. So this becomes 2 plus 1. Of course, do not forget your constant of integration. Since we've already applied the power formula, we no longer need to find the integral sign because this is already an integrated function. So we need to add, however, the constant of integration. This is already your final answer. However, you must perform some simplification. So 2 plus 1, of course, is 3. So this is now the final answer, x cubed over 3. In our introduction video, this is actually 1/3 multiplied by x cubed, but that's the same with x cubed over 3 plus c. So that is how we get the integral of a function using the power formula. So it's quite easy, right? So you just simply find the value of u, du, and n, and you just follow the right side of the equation, and then you now have your answer. So no more guessing for integration. Okay, so is that clear? By the way, if you are having a hard time following the discussions of the problems, you can, in your own time, pause the video, right? Repeat a certain section before you proceed to the next problem. But I will continue as is discussing the next examples, and you just take time, or take your time, or pause on your own. Okay. So with that, let's proceed to problem number 2. Okay, so example number 2. So this is a bit different from number 1. Okay, so here's our problem. We need to evaluate the integral of, what is this? Quantity 3x squared plus 2 close quantity dx. Okay, so if your first instinct is to use the power formula, okay, right off the bat, uh, you might want to consider first using the properties of indefinite integrals. So as you recall, we have 3 properties of indefinite integrals discussed and were recalled a while ago. So what were those properties? First, that is integral of du is equal to u plus c. And the second one is that it states that the integral sign is distributable, meaning if there are terms, okay, inside a certain integration symbol, they can actually be integrated individually, meaning you can distribute the integral sign per term together with the differential. So this term, quantity 3x squared plus 2, can be broken down into 2 separate integration problems, which are the integral of 3x squared, so distribute dx, and the integral sign to 3x squared, plus the integral of, so distribute dx to 2 and the integral sign to 2 plus 2 dx. Okay, this is the integration property of indefinite integrals. However, I must warn you that this distribution cannot or can only be performed if, okay, in the parentheses there is no existing power, meaning here the term, okay, these two terms are not together raised by an exponent, right? So if this, or if there is an exponent here, let's say for example quantity 3x squared plus 2 close quantity raised to 2, you cannot distribute dx and the integral sign. You're going to break a law in mathematics, okay? So the distribution is only allowed if and only if there is no exponent for the parentheses, okay? So now that we've distributed, we can now integrate individually. So we integrate 3x squared dx, and then we integrate 2 dx. However, there is still another property for integral or indefinite integrals that we can use. What is that? That is the third one. It says that if there is a constant term, right, inside of the integral sign, you can actually factor it out. So we can factor out 3 out of x squared dx. So it comes outside of the integral symbol. And here as well, we can factor out 2 out of dx. So it comes outside of the integration symbol. This means that 3 and 2 will no longer be included when you integrate the terms inside, okay, the integration or the integral sign. Instead, what will happen is that you integrate what is inside the integral sign and you simply multiply 3 and you simply multiply 2, okay? So if you remember integral of x squared dx, this was our first problem, correct? So using the power formula, we got x squared dx as x cubed over 3, okay? So the integral of this is now x cubed over 3 multiplied by the factored out 3 a while ago. And of course, the integral of dx, right? So the first general property of integration, the integral of du is u. Therefore, the integral of dx is x. So this becomes 2, the factored out 2 multiplied by x. And of course, don't forget the constant of integration plus c. Now, you might be wondering, there are 2 separate integration processes here, but there is only one constant of integration. Now, it's actually okay. You know, you don't need to write multiple c's or multiple constants of integration, okay? Because this c is already symbolic of the possible constants that may be present for the 2, okay, or 2 or 3 more terms. So just one c. So as a rule, or as for simplicity, you can write c or plus c on your final answer only. So don't write individual c's for individual integration of the same problem, okay? So if you try to simplify this, 3 can be cancelled out. So this can become x cubed plus 2x plus c. Now, you might be wondering, how do we check our answers for integration? So if you remember, integration is the inverse of differentiation. Meaning, if we derive or if we differentiate our answer for integration, it should go back to your original problem. So if you remember differential calculus using the power formula, how do you derive x cubed? So power formula for differential calculus is 3, right? N multiplied by u raised to n minus 1. So 3 x, 3 minus 1 is 2, that is 3x squared. Derive this plus 2x. Exponent of x here is 1, right? So 2 times 1, that is still 2, times x raised to 1 minus 1, x raised to 0 is equal to 1. Anything raised to 0 is 1. So there you have your 3x squared plus 2. C is a constant of integration, so it will not have any more values here. So that is our second example. Using the power formula, but also using the properties of indefinite integral. Okay. So again, if you have a hard time following the discussion, you can take it at your own pace. Meanwhile, I'll proceed to the third example. So example number 3, okay, this time we have three terms, 2x cubed plus 5x squared minus 4 quantity dx. Take note, there is no power here on the parentheses, meaning the integral sign and the differential x can be distributed individually among the three terms. So if we do that, this now becomes three individual integration process. This is now integral of 2x cubed dx plus integral of 5x squared dx minus integral of 4 dx. Minus because the sign here is negative. Okay? So again, property number 3, if a constant is inside the integration symbol, integral sign, you can factor it out and just multiply it later to the integral. So factor out 2 here, factor out 5 here, and then factor out 4. Okay, now we have these three integration to perform. So let's start with integral of x cubed dx. Again, we are still on the power formula, right? So how do we integrate x cubed dx? Well, you need to identify which is u, which is n, and then which is du. Never mind first x squared and dx here. We're only after this, or we're only going to solve first this problem, okay? So in this term, x cubed dx, which is your u? Your u obviously is x. What is the exponent of your u? So the exponent of x is 3, therefore our n is 3, right? And what is the differential of x? The differential of x is dx, therefore dx is now du. So all of the components of the power formula are present here, or are now well defined or identified here. So we can now translate them to the right side. So what you do is simply copy u. Our u is x raised to what? N plus 1. So 3, that's our n. Add 1, that is 4. All over the same, n plus 1 all over 4. And that is now your integral of x cubed dx. We do the same thing here. So again, we have x squared dx. Our u is x. Our n is 2. Our du is dx. So all of the terms or components of the power formula are present. So you can now proceed to the right side to solve for the integral of this term. So this now becomes x u n plus 1, 2 plus 1, 3 all over n plus 1 over 2 plus 1, 3 as well. Okay, and then simply multiply the factored out 5 here. Of course, the integral of dx is x. Okay, so simply multiply 4. Now you can simplify further. So 2 over 4, that is 1/2. So 2 over 4, 1/2. This becomes x raised to 4 over 2. Then plus 5 over 3. Unfortunately, there are no fraction that is more simple than 5/3. So you retain 5/3. And then minus 4x. Of course, do not forget plus c, the constant of integration. Now, if you'd like to check the answer, you simply derive this equation, okay, or differentiate this equation with respect to x, and I can assure you, you're going to return to the original problem. So that's how you know your answer is correct, okay? That is the third example for the power formula, okay? So if you have any questions, you kindly keep your questions in mind, and you can ask them later on. So next, we proceed to example number 4. For example number 4, now this one is a bit different, okay? Because there are now a lot of terms. So we are to integrate what? We are to integrate x squared quantity x cubed minus 1 closed quantity raised to 4. Okay? So how do you proceed in using the power formula? First, check if you can simplify the problem using the properties of indefinite integrals. Okay? What are those? You can try to distribute dx and the integral sign. However, as I've mentioned a while ago, if the parenthesis has an exponent, okay, you cannot distribute the integral sign and the differential. So that property cannot be used here, unfortunately. Are there any constants that can be factored out? None. Okay. You cannot factor out variables or functions out of the integral sign because they are the one that you need to integrate. Okay. So let's try to use the power formula. Now I told you a while ago, u, okay, can be any function. So u can be any function. A function can be a single term, can be a binomial, or can be a polynomial, or multiple terms. Correct. So here, if you're going to choose for a u, I suggest, okay, so my suggestion is you're going to choose for a u with the higher degree because you can choose x as your u, or you can choose x cubed minus 1 as your u. Out of these two, okay, the highest degree is x cubed, okay? So x cubed has the highest degree, so I would suggest you use u equal to x cubed minus 1. X cubed minus 1, not just x cubed, no, okay? Because this term is the base of 4 with an exponent of 4. Remember, u or n is the exponent of u, therefore u is the base of n. Here, 2 is the exponent, x is the base. Here, 4 is the exponent, x cubed minus 1 is the base, not just x cubed, okay? So we're going to choose u equal to x cubed minus 1. So we have now u, x cubed minus 1. Therefore, the exponent of x cubed minus 1 is 4. So our n is 4. So we now have u raised to n. Therefore, our only remaining component missing is d sub u. So if you solve for d sub u, you're going to differentiate with respect to its own variable, u. So x cubed minus 1, if you try to differentiate this one, so x cubed, when you differentiate it, it becomes 3x squared dx, right? Minus 1, constant differentiated is 0. So this is now your du, 3x squared dx. So you need to check now if this term is present in your problem, okay? So let's see. Is dx present in the problem? Yes. So dx is there, correct. Is x squared present in the problem? Yes, so there is an x squared there. You can simply transpose x squared here right next to dx, right? Multiplication. However, we are missing 3, right? We cannot use the power formula if there is a missing component in your missing factor in your components. Du is very specific. Du must be 3x squared dx. Not just x squared dx. Meaning you can no longer proceed with power formula if 3 is missing from the original problem. Okay? So how do we integrate with this? Well, we now need to introduce a balancing factor. So if we need 3 here, right? If we need 3 x squared dx and we only have x squared dx, we simply need to multiply 3 there, right? So we multiply 3 so that we now have the term du, 3x squared dx. However, when you multiply 3 to the integrand, you actually change the value of the integral itself, right? For example, 3 times 1 is now 3. The value has now changed. The value or the problem was now changed. But you're not asked to integrate 3x squared quantity x cubed minus 1 raised to 4 dx. You're only asked to integrate x squared quantity x cubed minus 1 raised to 4 dx. But you needed to add 3 here. So to cancel out or to balance these 3, we must also divide the equation by 3. So what happened? We multiplied the equation by 3, and then we also divided it by 3. So in reality, nothing changed when it comes to the value of the integral. This, for the lack of a better term, is our balancing factor. So we're going to call this our balancing factor, okay? So it's as if we multiplied 3 because we needed 3 for du. So we also divided by 3 so that we do not change the actual problem itself, okay? So we call this our balancing factor. So you now have 1/3 here, you now have 3 here. 3 multiplied by 1/3 is simply 1. So 1 multiplied by the original problem, that does not really change the problem itself. Okay. So with that, we can now proceed with our integration. So we now have du. Unfortunately, we need to add now 1/3. So this will now become, or we will now have 1/3 outside of the integral sign. So do we now have u and du? Yes. U is x cubed minus 1. N is 4. Du is 3x squared dx. Okay, so simply follow now the right side of the formula. So this becomes u raised to n plus 1. Our u is x cubed minus 1. So x cubed minus 1 raised to n, that is 4, plus 1, so that is 5, all over n, okay, 4 plus 1, that is 5. Do not forget the 1/3, okay, 1/3 was our balancing factor. So you can simplify, that is 1 over 3 times 5, or simply over 15. So our final answer therefore becomes x cubed minus 1 raised to 5 over 15, plus of course the constant of integration. Okay, so this was a very good problem in showing you how to identify properly your u, your n, and how to modify, okay, the equation without changing its value to bring out your desired du. Okay, so I hope that was very helpful for you. So again, in choosing u, first you try to identify the highest of degree between the two bases. Okay, so I chose x cubed minus 1 because it has a high degree of 3 compared to x with a degree of 1. Okay, so that was example number 4. Okay, now so we have our last example for the power formula. So this one is a bit different because the binomial, okay, inside the parenthesis is now raised to 2, or has now a power of 2 dx, correct? And we only have one base. The base is now 1 minus 2x squared, unlike in example number 4, we had 2. So this time, how do we use the power formula to solve this problem? Well, I told you that you cannot distribute the integral sign if there is a power on the parenthesis, because that will break a rule in mathematics. So what you can do is you can simply eliminate this first so that you can distribute the integral sign easily. So how do you do that? So in your elementary college algebra or algebra, you should have learned how to expand binomial. This is a binomial because it has two terms. First term is 1, second term is negative 2x squared. And this binomial is raised to 2. So if you perform binomial expansion, this becomes 1 minus 4x squared plus 4x raised to 4 quantity dx. So this equivalent trinomial is the expanded binomial. Okay, so kindly refer back to your binomial expansions topic in your elementary or college algebra. Okay, so this trinomial because there are now three terms, is no longer raised to a power, it's only raised to 1. So what we can do is we can now try to distribute the integral sign individually into these three terms and then integrate them one by one. Okay, so 1 dx, that is integral of dx, minus, okay, integral of 4x squared dx plus the integral of 4x raised to 4 dx. Okay, this is now the distributed integral sign. But we can simplify the solution further by employing the use of property number 3, which is factoring out a constant out of your integral sign. So this 4 can be factored out of the integral sign. This is supposed to be an integral sign, okay? Integral of x squared dx. This 4 can also be factored out of the integral sign, leaving you with 3 integration process. So the integral of dx is obviously x, minus the integral of 4 x squared dx is again 4 x cubed over 3. How? We use the power formula, okay? And then integral of 4 x raised to 4 dx, that is 4 times x raised to 5 over 5. So you refer to the power formula on how we got these integrals, okay? So simplifying further, you can simply bring out or bring inside or on the numerator 4. So that is 4. There's supposed to be a parenthesis here. So parenthesis, parenthesis. So the simplified answer is x minus 4x cubed over 3 plus 4x raised to 5 over 5 plus c. However, this can also be represented as x minus 4/3 multiplied by x cubed plus 4/5 multiplied by x5 plus c. So they are both correct. Okay, they are accepted answers. Okay, so that is it for our examples for the power formula. So I think I'll leave you with an example that you can try on your own. So see if you can solve this one. So example number 6, you can try this on your own. Try to solve this one. So this is the integral of the square root of y, okay? The square root of y multiplied by 1 plus y close quantity dy. Okay, so how do you now solve this problem? The square root of y multiplied by 1 plus y quantity dy. Okay, so it's up to you how you attack the problem. The solution for this example will be given on the next video. Okay, so as always, if you have any questions, you can leave it down on the comment section below. But before we go, let's review some concepts that we've learned related to the power formula. So all of the components of the power formula must be present, again, must be present before you use the formula itself. If not, then a balancing factor or a modification of the formula must be introduced, okay? Balancing factors, okay, the term that we multiply and divide to the integral, must be constants only. These are not, okay, variables, or these are not terms. Again, a term, a variable, cannot be a balancing factors. Balancing factors are exclusively numbers or constants, okay? And of course, remember that n must not be equal to -1. So in our example, we have not encountered a problem wherein n is equal to -1. But as we go along to the other formulas, you will discover that there are other problems where n becomes -1, therefore leaving the power formula invalid. Okay, so these are the important concepts that you must remember in our Unit 2, the power formula. So if you have any questions, you can ask down the comment section down below. So I hope that was helpful, and then see you on the next video. Thank you.